What is it that attacks railways, oil rigs, roller skates, Rolls-Royces, nuclear reactors and rat traps? The answer is rust. Corrosion, which is what this film is all about, is all around us. It's even, as anyone with a duodenal ulcer will tell you, it's even inside us. It's really high time that someone invented stainless steel.
Anyone who invented stainless steels today and called them stainless steels would be had up under the Trade Description Act, because if you put them in the wrong environment, they will corrode.
You can see here, that's stainless steel. But stress corrosion has broken up all the fine mesh so that it becomes absolutely worthless. People often try to get cures instead of thinking about prevention earlier. I think, in fact, the attitude of industry, lots of companies, is they think of the corrosion story a bit like we think of the National Health Service. Really, a lot of people, we really have a national disease service in this country because we only go when things go wrong. Yeah. And I think corrosion is the same sort of thing. People wait often longer than they should before they could take some action.
Corrosion will attack any metal. And metal is at the heart of our civilization.
You?
Yeah, right. Looks in a pretty poor state already, this car, doesn't it, from up above?
Well, it is, but now this is the type of vehicle that can be made to look really good appearance from the outside. The problem is, of course, under here with all these holes.
Yeah, it's certainly in it. Oh, that's nice, isn't it?
In the job that I do, inspecting cars day in and day out, I find out what the car is, and then I know that where that corrosion and where the problems are going to be with the vehicle, because each vehicle has its own problems in one direction.
When you get a thing like this fracturing across, it hasn't actually rusted all the way through then.
No.
It's a combination of two things, is it?
Yes, various corrosion around that area causes weakness, and this weakness causes fatigue fractures, and something will go. It will be, well, it's hard to say what will go first on here. Either the subframe will collapse here, or the body will collapse around the subframe, or maybe the suspension will go. So it's anybody's guess. It's a real danger on the road, this vehicle.
To most of us, corrosion is the clatter of an exhaust pipe disappearing into the night, or a finger through the rusty wing of our beloved 1953 Morris Minor. All flesh is mortal. It happens sooner or later. Later if you live in the Sahara, sooner if you live near the sea or you do a lot of driving along salt-caked motorways. But corrosion in cars is really only the tip of a rotting iceberg. A small hole that costs a few quid to put right if it happens in a car can cost a loss of precious fluids, a day's production, even a loss of life if it happens in a chemical plant. And what's flowing through these pipes here is a good deal more aggressive than rainwater or even sea spray. So it's hardly surprising then that almost every industrial country in the world is spending more each year to fight corrosion, our own included. Among the world's front runners in corrosion research is the University of Manchester Institute of Science and Technology, UMIST. The Corrosion Protection Centre here has a triple role: to teach, to research, and to provide practical help to industry. The experiments simulate real-life problems. Some of the most primitive-looking produce the most complex results, and the range of work hints at the universal nature of corrosion. Over the years, the centre has collected some awful warnings from the least likely places. Dr. Peter Elliott.
Typical example from the domestic scene, we can see here the effects of prolonged storage from a pickle jar where the concentration of the contents has led to this rather sad appearance after storage in the kitchen or on the shelf in the back of the cupboard that people tend not to look at so often. You can see the problems in the home reflected in industry. Aluminium is very good. If the reference books say aluminium, water, excellent. So why does aluminium get all the holes from a stirrer used in a small bath? In this case, the water bath was being heated by copper coils. The copper went into solution and precipitated out on the surface and produced the dissimilar metal contact. Small copper area, large aluminium area, active corrosion, holes.
But airliners are made of aluminium, and whoever saw a rusty airliner? In fact, what we notice most about aluminium as compared to steel is that aluminium doesn't seem to corrode. You missed Dr. Robin Proctor.
Metals resist corrosion for two reasons. Either because they are inherently resistant to corrosion, for example, gold, or because they form a corrosion product which prevents further corrosion. Now, if we take the case of carbon steel, in the atmosphere or in seawater, this rusts, and you get a voluminous corrosion product which is not in the least protective. On the other hand, if we alloy that with something above 13% chromium, which gives a stainless steel, we get a completely different corrosion product. We get, formed on the surface of the stainless steel, a very thin oxide layer.
That thin oxide layer is what protects aluminium too, but this nice shiny piece has been painted with a chemical that stops the passive film forming, and it's corroding before your eyes. Before we can understand why metals corrode, we have to take a brief intermission for a basic chemistry course. Basic chemistry course. Lesson 1. An element is a substance that can't be broken down into any other substances, and there are over 100 of them. For instance,
there's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
Lesson 2. Of those 100+ elements, only half of them are metals. And of those, a very small number are commonly found in day-to-day engineering. Lesson 3. Basically, metals corrode because, apart from gold, they just ain't natural. Metals don't lie there shining in the ground. They're almost all dug out as ore. Iron ore is ferrous oxide. That's iron and oxygen combined, and the oxygen has to be driven out by heating the ore. The end product is the pure metal, but the oxygen in the atmosphere tries to recombine with the iron, and when it does, ferrous oxide forms again. That's the same natural state as the metal started from. In other words, it goes from rust to rust.
And all metals, certainly all metals in common usage, are trying to do this all the time. The only exception is gold, which, as everyone knows, doesn't corrode. That's why we have gold ornaments, why gold ornaments dug out of the ground have lasted for many years.
This plant makes sulfuric acid. It's very aggressive stuff, so gold would seem to be an ideal material for all that piping, except, of course, that it would be a little pricey and structurally a little feeble. At the same time, the wrong metal could go as fast as our corroding aluminium did. So while gold is out, using the right material is all important. Dr. Tony Richardson is a materials engineer for Britain's biggest chemical company.
Yes, I think there are corrosion problems in all industries, you could say. It doesn't matter whether you're building bridges or building ships or offshore structures, or you're building, in my case, chemical plant. There must be a materials input to the problem, because inevitably structures do deteriorate. And given one of the main aims of capital investment, which is to make the optimum use of capital, what we're continually trying to do is to select the right material for the job. And that basically means ensuring safe and reliable operation for the design life of the structure, whatever it be.
This plant has sulfuric acid running through these pipes at a rate of 1,200 tons an hour. It's 98% pure at a temperature of 75 degrees centigrade. Hence the need for the goggles. Hence also the need to know exactly what is happening in this plant in terms of corrosion. Now, fortunately, there are ways of measuring that, and this is typical of the sort of probe that is used under this kind of condition. Inside the end there is a little loop of wire of known resistance. A current's passed through it, and the current coming back is measured, and then the resistance of that wire is compared to the resistance of a similar piece of wire which is well away from the process, so that the rate of corrosion can be relatively fixed. Now, the actual probe which is fixed into this pipe here works on a slightly different principle. At the end are electrodes which measure the tiny electric currents which are produced whenever there is corrosion. Those electric impulses are read off on a host of dials in the control room. The rate of corrosion they show has already been predicted. It's only the unexpected reading that would disturb the productive car. Closing down any plant is an expensive business. UMIS's latest piece of detective work is on a 30-metre length of oil pipe with a suspected corrosion problem from a New World oil field. And its absence from the scene is costing the company something like £30 million a day. But then the oil industry does have special problems. There's an awful lot of metal here to look after, but at least it's relatively easy to get at. Now, this plant is something like, well, something under 100 feet high. But imagine one which was 700 feet high. It's not actually too easy to imagine, but in fact that's taller than the Post Office Tower in London. And now imagine it with 600 feet of it standing in salt water and exposed to gale force winds. Well, that particular corrosion engineer's nightmare is called an oil rig. North Sea oil was hailed by some as the saviour of Britain's economy, but the hostility of the environment has taken the gilt off the gingerbread more than once and has certainly taken most people by surprise. On the 27th of March 1980, the Alexander Keeland, a rig supporting a floating hotel, lost one of its 5 legs in a very moderate gale and toppled over. 123 men lost their lives. It's this kind of structural failure that haunts the rig builders, and one of the prime causes is corrosion. This is a tiny piece of the metal used to build the rigs, mild steel, in a tank of seawater. A dye shows up any dissolved metal. Billions of times bigger, but basically no different, is this North Sea oil rig.
We're not terribly concerned by simple metal loss on a structure. There is severe concern when it happens, but the killer is corrosion fatigue, which leads to perhaps catastrophic failure at a welded joint.
Specialist companies have come into being who install the technology to fight the corrosion nightmare. Brian Wyatt, a director of one of them, knows the problems.
There are a number of problems which are rather particular to the North Sea. Some of the fields have very high producing oil temperatures, some in excess of 100 degrees centigrade. and the pipelines carrying this oil clearly are running hot. The corrosion rate is increased almost proportionally with the increased temperature. There are additional problems with coatings on those pipelines, and there are problems with the anodes that we fit to those pipelines, particularly where they're buried in mud.
The anodes that Brian Wyatt is talking about are what stop these oil rigs dissolving. In practice, they're huge aluminium ingots, up to half a ton in weight, strapped on to the vulnerable legs of the rigs and providing what's called cathodic protection. The natural phenomenon that makes them work is a particular interest to another UMIST scientist, Dr. Vic Ashworth.
Well, quite simply, when corrosion occurs, there are two essential things that go on. First of all, the metal dissolves, clearly, and that's what we understand as corrosion. But to a corrosion scientist, he's aware that there's also a current flowing in the metal from the point of corrosion into the bulk of the metal. So there's always this tiny corrosion current flowing. If you haven't got the current, you haven't got corrosion. And if you have got the current, then you have got corrosion.
Yeah.
And what we're trying to do in cathodic protection is to back off that current so that you have no current, therefore you have no corrosion.
What are these bits that are actually hanging down into the water? What do they represent?
Well, this is a piece of mild steel, or at least down the bottom we have a piece of mild steel which represents our oil production platform. This electrode here is a piece of platinum, and it's our means of getting our current into our piece of steel. On an oil production platform, that would be referred to as the anode, and you can see at the moment that with our current passing between this anode to our structure, we don't have any blue developed, so there's no corrosion, but we do have some gas coming off the electrode.
So does that mean that the situation you've got now is the one that the man who owns an oil rig is keen to see?
Oh, certainly. That's exactly what he wants.
Yeah. So at the moment, you're putting a current through which is opposing the natural flow of current that you get with corrosion.
That's exactly right, yes.
And what you're going to do now is actually to give a bit of a boost to the natural flow of current in corrosion. So we should see that.
Just simply by reversing the current, and let's see if that happens now.
So what we're seeing there is actually steel dissolving in salt water.
That's right. That's right, yes. And that is going on all the time when steel is in salt water, if it's not protected.
On a North Sea oil rig, a generator would provide the protective current. It's called the impressed current system. Another technique uses the natural corrosion current to stop corrosion. This piece of steel isn't protected at all, and you can see the rust on the bottom. But an identical piece in the same tank is defended by what's called a sacrificial anode. In this case, it's a piece of aluminium corroding in seawater, and it's connected to the steel plate as would happen on an oil rig. The current from the corroding aluminium blocks the current that's trying to flow in the steel, and even though the mild steel is in salt water, it doesn't rust at all.
Well, with cathodic protection and the right design, we can virtually assure that 15 to 25-year life. Without effective cathodic protection, even partially ineffective cathodic protection, we may be in a situation where in 2 to 5 years there are severe problems with the structure. Another one of the problems is that the cost of rectifying a defective cathodic protection system can be astronomical, talking about major deep diving activity, for instance, and whereas a cathodic protection system on a fixed offshore structure may cost £1 million to install in the yard, you may be talking £30 million offshore.
The message for the oil industry is get the science right and use it properly, because once a rig is in the North Sea, it's almost out of reach. Another futuristic piece of UMIST research concerns the same sort of problem, but on a very different scale. What you're watching here is an artificial hip joint implantation. The new joint is made of metal, and like the North Sea rigs, once it's in its environment, it may be subject to unexpected corrosion, and retrieving it is highly undesirable. This sort of new technology is calling for an entirely new approach. This is an isotope separator owned by Salford University, with whom UMIST is cooperating in the search for hitherto impossible metal alloys. This, for instance, is steel with chromium dissolved in it to make the alloy we call stainless steel. This is copper with tin dissolved in it to make the alloy bronze. But some metals, however desirable their combined qualities might be, just can't be dissolved together. Tantalum, for instance, won't dissolve in iron. It's the same here. Sugar dissolves easily in water. Sand will never dissolve in water. You could only get a sand solution by planting individual atoms of sand in the water, which sounds impossible. Basically, though, it's what the combined UMIST and Salford teams are trying to do with metals. Dr. Bill Grant heads research into iron implantation at Salford University.
That's right. Well, the first thing then that you need to do is to take the material that you want to make as an ion beam and get it into the form of atoms. And then, if you can take from that atom just one electron, then you have yourself a positively charged ion. And that positively charged ion, if placed in an electric field, can be accelerated. So the process is simply one of getting an atom, removing an electron, a positive ion, putting it in an electric field, which accelerates it. And this then gives you a beam of charged ions, or a beam of particles, which you can direct towards the target that you're interested in.
A cylinder is filled with vaporized tantalum. A wire runs inside the cylinder and 40,000 volts is pushed through it. This excites the tantalum particles so that their atoms lose an electron and become those positively charged ions. They hurtle out of a slit as a stream of particles into a vacuum tube. Above and below the tube are very large magnets.
A mixture of particles, or ions, pass into the magnetic field. But then they're all bent, and the degree to which they are bent depends essentially on their mass. So the heavier ones are bent to a certain degree, and the lighter ones to another degree. The magnet is used for purification, to separate out the ones you're not interested in, and it also helps to direct the beam and focus it, bring it to a nice sharp position on the target. You can envisage what's happening as just billiard ball effects. But if you imagine the target to be a set of billiard balls and the ion another billiard ball, it simply penetrates, scatters about, knocks some of the target atoms around, and eventually comes to a halt. Now, in a metal, this ion, which needs an electron, will normally pick up an electron from the metal. And so it resides eventually within the target as a neutral atom.
So in our hip joint, the tantalum will have been fixed, dissolved as it were in the stainless steel, creating an alloy with perhaps better wearing and corrosion-resistant properties. A miraculous alloy that in theory can't exist. Today at UMIST, the research work is taking them deeper and deeper into the details of just how corrosion behaves in the quest for the total understanding that will allow them to face up to industry's challenge as new technologies, new materials, new applications bring new problems of corrosion.